Today we're going to be looking at addition of nucleophiles to alpha-beta unsaturated carbonyl compounds, or ones in which there is a carbon alpha adjacent to a carbonyl carbon, and beta, which is the next carbon in the chain. If the chain were to continue, we would call the carbon after that the gamma carbon, the delta carbon, and so on as the letters in the Greek alphabet. Again, carbonyl, next to the carbonyl is alpha, beta. So alpha-beta unsaturated carbonyl compound in which the pi bonds are conjugated with each other. Now we know already that carbonyl compounds are polarized in such a way that the oxygen has a delta minus and the carbon has a delta plus. We can show this through resonance, and because of this we know that nucleophiles tend to attack the carbonyl carbon. But what about an alpha-beta unsaturated carbonyl? What does a nucleophile do when it encounters one of those? Let's take a look at a molecular model of acrolein, a 3-carbon alpha-beta unsaturated carbonyl compound. So here's your oxygen, carbon, carbon, and carbon. The electron density diagram here, you can see that the oxygen definitely has a delta minus on it. It's red. But both the carbonyl carbon and the beta carbon appear to have a delta positive on it. Let's see if we can figure out why. Again, we know that the carbonyl carbon is polarized towards oxygen. In fact, we can draw a second resonance contributor in which we show a formal positive charge on the carbonyl carbon and a negative charge on the oxygen. And we just change where the pi bonds and lone pairs are. So in this particular resonance form, we haven't changed the pi bond between alpha and beta. We have moved the pi bonding electrons from the carbonyl bond such that the carbonyl carbon now has 3 bonds and a positive charge, and the oxygen has a negative charge. Now, in fact, there is a second resonance contributor here because of the conjugation between this carbocation and this pi bond. And we can imagine the pair of electrons in this pi bond moving over to help stabilize the positive charge by forming a pi bond between the formerly carbonyl carbon and the alpha carbon. Like our negative charge would remain on our oxygen atom, and our positive charge would be located on our beta carbon atom because it would now have 3 bonds with no lone pairs. So in fact, there are 3 important resonance contributors for the alpha-beta unsaturated carbonyl system. And if you look carefully, you'll see that there is indeed a lot of delta minus charge on the oxygen atom. 2 of the 3 structures show minus charge on oxygen. And there is delta plus character shared between the carbonyl carbon and the beta carbon. So when a nucleophile comes along to react with an alpha-beta unsaturated system, it has 2 choices. It's attracted to both the electron deficient delta positive beta position as well as the carbonyl carbon, as indicated by the blue line to the beta position and the yellow arrow to the carbonyl carbon respectively. Turns out that some nucleophiles prefer to add in the beta position and some prefer to add directly to the carbonyl carbon. Now when nucleophiles add directly to the carbonyl carbon, this is actually the same reaction that we've been using for quite a while. In which the nucleophile adds directly to the carbonyl carbon, the pair of electrons from the pi bond gets kicked out onto the oxygen atom, resulting in a new bond between the nucleophile and the carbonyl carbon. Normally this intermediate then would undergo protonation in a second step, and we would end up with an alcohol product. This is the same direct nucleophilic addition that we've seen for reagents such as sodium borohydride, Grignard reagents, and so forth in the previous chapter. This reaction works when the nucleophile is one of our so-called hard nucleophiles, the ones with the concentrated negative charge on a single atom, such as alkylithiums or alkyl-magnesium bromides, Grignard reagents, or our hydride reagents, sodium borohydride, lithium aluminum hydride. Other nucleophiles would prefer to react in the beta position. That is, they're attracted to the delta plus at the beta carbon. Once the beta carbon is attacked, the electrons of that alpha-beta bond, move out of the way, and again we get a negative charge located primarily on oxygen. We end up with a new bond between the formerly beta carbon and the nucleophile. No formal pi bond shown between alpha and beta, and we actually have two resonance forms for the intermediate that results. One, shown here, has the negative charge located on the oxygen. The other resonance contributor shows the negative charge on the alpha carbon atom. This is actually an enolate ion. Enolate ions are important intermediate in one of the upcoming chapters, but they represent one of the three kinds of fundamental reactivities of carbonyl compounds. In any case, the new sigma bond is formed between the nucleophile and the beta position, and after protonation, we get a net addition of the nucleophile and the hydrogen across the beta-alpha bond, with the nucleophile at the beta position. So this is a case in which a nucleophile adds to an alkene, and it only happens when that alkene is conjugated to a carbonyl, such as in our alpha-beta unsaturated carbonyls. Nucleophiles that do this beta addition are known as soft nucleophiles and include such nucleophiles as dialkyl lithium cuprates and neutral amines. In Chem Activity 23D, we will look at working through the mechanism for this reaction for beta addition and look at other typical nucleophiles that react beta rather than direct carbonyl addition.